Sagittarius A*, the supermassive black hole anchoring the center of the Milky Way, has been a focal point of astronomical mystery and intrigue. Recent groundbreaking research from the University of Nevada, Las Vegas, offers a thrilling new perspective. This cosmic giant may have formed through a colossal merger of two black holes. In this video, we'll delve into this exciting discovery, explore the underlying science, and discuss its profound implications for our understanding of the cosmos. So without further ado, let's get started. Evidence from recent observations and simulations suggests that Sagittarius A* is not your run-of-the-mill black hole. It is a supermassive black hole with a mass of about 4 million times that of our Sun, situated roughly 27,000 light-years from Earth at the heart of the Milky Way. In 2022, the Event Horizon Telescope, EHT, made a monumental breakthrough by capturing the first direct image of Sagittarius A. This achievement, made possible through an international collaboration that combined data from radio observatories worldwide, has provided new insights into the behavior and characteristics of supermassive black holes. Building on these observations, researchers Yahan Wang and Bin Zhang analyzed the peculiar rapid spin and misalignment of Sagittarius A* in relation to the Milky Way's angular momentum. Their findings suggest that these characteristics are best explained by a major merger event, specifically a collision between this black hole and another supermassive black hole from a satellite galaxy. By using sophisticated simulations, the study demonstrated that a 4-to-1 mass ratio merger with an angular inclination of 145 to 180 degrees could accurately reproduce the observed spin properties of Sagittarius A. This scenario suggests a dramatic interaction that significantly altered Sagittarius A*'s mass and spin orientation. If Sagittarius A* formed through a massive merger, it would profoundly alter our understanding of the Milky Way's history. The research suggests that such a merger could have occurred around 9 billion years ago, following the Milky Way's collision with the Gaia Enceladus galaxy, a smaller satellite galaxy that brought its own black hole. This points to a period of significant gravitational interactions, which would have reshaped the orbits of stars, gas, and other materials in the galaxy. This concept reinforces the hierarchical merger theory of supermassive black hole growth, indicating that galaxies and their central black holes evolved together over billions of years through chaotic and sometimes violent processes. The aligned high spin observed in Sagittarius A* suggests a history marked by dramatic events rather than slow, steady growth. In essence, this discovery invites us to rethink how we approach models of galaxy dynamics and black hole development. So why is this so crucial? It challenges our existing paradigms and offers a new framework for studying black holes and their role within galaxies. The implications stretch beyond our Milky Way. If similar mergers have shaped other galaxies, we could better understand the broader cosmic architecture. Looking forward, this research opens the door to a new era of observation and discovery. With space-based gravitational wave detectors like the Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, we will soon have the tools to detect gravitational waves from mergers of supermassive black holes throughout the universe. The recent advancements with the Event Horizon Telescope will complement these efforts by enhancing our ability to directly image black hole environments with unprecedented clarity. In recent test observations, the EHT achieved a higher resolution by operating at a shorter wavelength of 0.87 mm compared to the 1.33 mm used for the original images of Sagittarius A* and M87. This advancement allows astronomers to produce images that are 50% sharper, offering more detail on the event horizon and surrounding phenomena. Achieving such high resolutions, up to 13 microarc seconds, which is like seeing a bottle cap on the Moon from Earth, reveals new properties of black holes that were previously blurred by gravitational effects. These enhancements are crucial for studying how black holes attract and accrete matter and how they launch powerful jets over vast galactic distances. As EHT founding director Shepard Dolman notes, future observations could shift from merely detecting black hole shadows to precisely measuring their sizes, shapes, spins, and orientations. This sharper, color vision of black holes will distinguish between the effects of Einstein's gravity, hot gas, and magnetic fields that feed black holes. What's particularly exciting is that the inferred merger rate from the Sagittarius A* study aligns with theoretical predictions, suggesting that we are likely to observe multiple supermassive black hole mergers in the near future. These observations will add a crucial piece to the puzzle of black hole evolution, validating the hierarchical merger model with real-time data. In parallel, the discovery of intermediate mass black holes, seen as the missing link between stellar mass and supermassive black holes, offers additional context. Recent detections of such mergers by LIGO and Virgo hint at a continuum of black hole growth stages, further supporting the idea that smaller black holes merge to form larger ones over cosmic timescales. Additionally, future upgrades to the EHT, including new antennas and improved detectors, aim to capture high-fidelity movies of the event horizons around black holes. These dynamic animations will show the material swirling around these immense gravitational wells, providing a real-time look into the behaviors of black holes and the phenomena they create, such as relativistic jets. By merging these different streams of research, direct imaging from the EHT, gravitational wave detections, and theoretical simulations, we are poised to enter a new chapter in our exploration of black holes and their profound role in shaping the cosmos.